Now, you've all been to conferences where that, actually, in fact, I've been to conferences recently where what I just did didn't work and we were fumbling around for 20 minutes. So thankfully, thank you for that. That worked seamlessly. On the subject of refrigeration, listening to the last talk, if you're talking about quantum computing, then you also have to talk about refrigeration, because quantum computers typically operate at quite low temperatures. And you're not using hot and cold water, but you're using helium-3 and helium-4. And one of the interesting things about helium, is anybody familiar with helium cooling? Oh, that's good. So helium-3 is the stuff that's in the atmosphere. There's not a hell of a lot of it, but there's some of it. And helium-4 is really, really rare. There's quite a lot on the moon, but otherwise you can only produce it the other way around. You can only produce it when you produce nuclear weapons. So pretty rare stuff. So I'm going to talk about quantum computing. There is, understandably, because I work for IBM, a slight IBM bias on my talk. I'll be talking about the IBM Quantum Computing Initiative. Stop laughing. So, May of 1981, that's at MIT. The really frightening thing is that in 1981, I was at university studying my degree in electronics, applied physics, and computer science. And I was actually getting close to graduating in 1980. I graduated in 1982. So this photograph is quite worrying. Thankfully, Albert Einstein is not on it, so I'm not that old. But Richard Feynman is on it, and quite a few other people who are no longer around. But we can say that was kind of, sort of, the birth of the idea of that might make sense to think about using quantum physics to do computing. And it stayed a kind of very abstract idea for quite a while. And it's only in the last few years that we've been in a situation where it's we actually have quantum computers. We're able to do computations with them. So this is the quote from Richard Feynman. Has anybody read this paper? I recommend it. Richard Feynman, has anybody read or used Richard Feynman's lectures on physics? Come on, I want to see some hands. Okay, so you know the guy was not just a good physicist, but he was also very, very good at communicating ideas. This paper is it's well worth a read if you want to understand the basics and fundamental ideas behind quantum computing. He also wrote a very good paper on negative or complex probabilities, which, to be honest, I still don't understand, even though I have a PhD in applied mathematics, but there you go. It was a long time ago. What's the power of quantum computing? Why is everybody talking about it? Why is it such a big topic at the moment? Well, classic computers, that's what you guys are all talking about. That's why high-performance computing is such an important topic. That's why such large amounts of money are invested in it. Because in order to double, or let's say the ability to solve problems scales linearly with basically the number of transistors on the chip, or the number of transistors in memory and in the CPU, or it doesn't matter. I mean, you can talk details, and a lot of this conference is about exactly how those details work: memory, CPU, communication, connectivity, all this kind of stuff. From a physics point of view, it's all dotting the I's and crossing the T's. I know you're going to all hate me for that statement, but that's basically what you're all doing here, is you're dotting the I's and crossing the T's to get better performance. But with a quantum bits, with qubits, there is a combinatorial relationship between the number of qubits and the size of problem you can attempt to solve with those qubits. And you notice something very, very cagey about the way I formulate things, because, of course, the devil is in the detail. And IBM talks about 16-qubit device, which you can access for free in the cloud. We also have 50-qubit devices, which you cannot access for free, which cost money. Various other companies, some big search engine company, beginning with G, they have some qubits as well. But the qubits are there. You can start to think about solving problems with them. But it's not easy. I'm going to talk in a little bit about why it's not easy. But you have this combinatorial scaling. Let's take an example. Caffeine. Who likes coffee? Okay. Which sick people among you don't like coffee? I'm prepared to admit it. Okay, coffee has 95 electrons. If you want to simulate or determine the energy state of a coffee molecule, you're going to need a lot of memory, a lot of CPU power in order to do that. That's one with 48. I mean, I'm not going to talk to the molecular simulation people here in the room about whether there's one or two zeros too many or too few here. Let's not dot the I's and cross the T's. It's a lot of computation power, a lot of memory. There's the molecule up there. And there's an IBM cup. Does anybody possess one of those? Are there enough people from IBM or used to be at IBM here? Some of you must. Okay. The number of atoms on our planet is estimated to be somewhere between 10 to the 49 and 10 to the 50. So we would need as much memory as between 1 and 10% of the Earth's mass. Now that's already been done. In Hitchhiker's Guide to the Galaxy, the planet Earth was actually a supercomputer constructed by deep thought to determine the question, to which the answer was 42. Unfortunately, it was destroyed by Vogons 10 minutes before it was due to deliver the answer, but I'm sure you all know that. So building huge supercomputers to basically, with raw force, solve problems has already been tried, at least in fiction. But what we could do, of course, is we could actually represent this using 160 qubits. 160 because log to the base 2 of 10 to the 48 is 160. You need 160-bit qubits to represent 10 to the 48 classic bits. That's the theory. Okay, we're a long way away from that. One of the challenges is the physics of actually building a quantum computer, getting it cold enough, getting the right way to represent qubits, measuring them. And the other, for me, although I did study applied physics many years ago, fundamentally I consider myself informatica in that context, is the algorithms, quantum algorithms. We need to rethink completely how we write computer programs. Basically, everything you ever learned about programming, I don't know, go in a smoke lodge or do some kind of cleaning ritual, but free yourself of existing programming models. They don't work and they don't transfer. The basic unit of information in quantum computing is the qubit. The traditional bit, you all know this, has two possible values, 0 and 1. Thanks to De Morgan's theorem and classic logic, we can do a whole lot with bits. That's your daily business. A qubit has a number of possible simultaneous values which you can take on. And it's not 0 or 1, but it's actually an undetermined complex number with magnitude between 0 and 1. Actually, no, magnitude 1. The state of a qubit, that means a state is in what's called superposition. So it can be simultaneously 0 or 1 or any other value in between. You can also entangle qubits. Has anybody heard of entanglement? Yeah, a couple of hands. Okay, so entanglement, well, this was the thing that Einstein really did not like. This was his, not his God does not play dice, but spooky action at a distance. He didn't like that. He found it physically not a pleasant idea that two systems could, when they're entangled, could share physically separate over a distance the same state. Since Einstein, I think it was the University of Peking, in collaboration with the Chinese aerospace, military, whatever, they've demonstrated entanglement with satellites. So they've taken an entangled electrons, sent one of them or sent some of them up into space, put them on a satellite, left the rest in the lab in Beijing, and measured an entanglement over several hundred kilometers. It works. And there's actually some experiments on the IBM quantum computer you can do to also show entanglement. So with n qubits, you can store 2 to the n bits. And what can you do with that? Well, with classical systems, you need bits to represent states, and you need you can only specify a state distinctly and separately. With quantum bits, with superposition and entanglement, you can represent all possible states, or let's say a large number of possible states, simultaneously. And one of the challenges, and this was brought home to me last night while I was eating dinner with some of you from Lenovo. This is the point where all your intuition goes out the window. All your ideas about data and how computers work and how computer programs work, you have to suspend those. Now, let's look in a little bit of detail about that. How does it actually work? Well, superposition, we take a number of quantum bits. In this case, we have 5 of them. So the 5 here, 1, 2, 3, 4, 5, which give us 2 to the 5 is how much? Gilad, what's 2 to the 5? 32. So we have 32 possible simultaneous states. And we put those individual qubits into superposition. Now, how do we do that? Well, each qubit, when it's initialized, we either initialize it as a 0, as a 1, or as a 1. And then, mathematically speaking, what we then do is apply a transformation, something called a Hadamard transformation. And actually, when I give this talk, I've got a note banning me from saying the word Hadamard, but you're all technical people, so I can do it. You apply a Hadamard transformation, which basically rotates that little sphere, this thing called the Bloch sphere, rotates it through 90 degrees. So it takes that 1 or 0, whatever it is, and puts it in a state of superposition. And if you do that with all 5 bits, you then have a system which is simultaneously in all 32 states. Okay. You can also entangle bits, so you can make 2 different qubits dependent on each other, which interestingly forbids you then from looking inside those 2 qubits. You can't look inside any of the qubits anyway, but in entangled qubits, in an entangled pair, the state of that pair of qubits is, even within the quantum system, indeterminate. So they cannot be described independently of each other. So now you've got a system in a simultaneity of 32 states. And the trick is to then work out a way of mapping your problem into a specific set of transformations which operate on those 32 states, or dependent on the number of qubits you have, however many states that is. That's the challenge. And that's the difficult part. Where are we going to see some applications? We're at the very, very start, really at the start. So at IBM, we are engaging with, talking to customers and academic institutions about exactly that step I just talked about. How do I use a quantum computer on real-world problems? And it's a big challenge. One topic where we're using quantum computers right now, so we have a 50-bit quantum computer in Yorktown. It's being used to simulate the state of a molecule. In other words, it's being used to directly do quantum chemistry. If we look at quantum computing in general, then we have, I would say, 4 main application areas. The first one is traditional algebraic stuff. So if you're using a supercomputer to do matrix, any kind of matrix operations, typically we think about factoring numbers, cryptography, that kind of thing. Then that's a potential application area for quantum computers. There's an algorithm called Shor's algorithm, which is designed to take a number and determine its prime factors. And for small numbers, it's extremely inefficient. You can go on IBM's quantum computing cloud service. You can play with the Shor factoring algorithm with 5 qubits or with 16 qubits and watch it underperform your laptop. But if at some point in the future, when I say no, I wouldn't say if anymore, I would say when, at some point in the future, we have maybe a few thousand qubits, then traditional cryptography, which is based on factoring large numbers, is going to start to be a little bit crackable. I was asked last night, when's that going to happen? This young man here wants to know. And I couldn't really answer him because it's, it might be 5 years. Well, I suppose it's not going to be 5 years, but it'd be 20 years, maybe 15. Not that RSA will be broken in 15 or 20 years, but that's the point where we're going to have to start to really have some viable alternatives to traditional cryptography. I mean, that's the other side of cryptography with quantum computing, is that traditional cryptography, how it's done today, is not robust if there are universal quantum computers. However, there are other ways of doing cryptography which are immune and resilient against quantum computers, quantum cryptography. So it's not the end of the world, it's just we're going to have to shift the goalposts. Of course, shifting those goalposts comes with a very high price, because in order to implement quantum cryptography, you have to have quantum computers. Obviously, nothing's for free. What does it look like? So this is a quantum computer on the left. Did you say Google? Yes, get out. Yeah, it does, doesn't it? Well, this bit down here, that's the business end. That's the bit that's at somewhere between 10 and 20 millikelvin. Have you any physicists here? So real physicists? Oh, come on, guys, you're all from HPC. There must be a physicist somewhere here. Oh, I'm disappointed. Okay, so to get, 10 millikelvin. Absolute zero is 0 Kelvin, obviously. The temperature of intergalactic space, okay? So not even interstellar space, but intergalactic space. There is nothing out there. Does anybody know what temperature that's at? Yes? Exactly. And why? Why? Exactly. The microwave background radiation represents equivalent heat, and that is 2.7 Kelvin. So even intergalactic space, which is as cold as it gets, is significantly warmer than the business end here, which is at, I mean, if you go on the IBM Quantum Experience website, it tells you what temperature the particular quantum computer is at. There are several of them. Typically, it's somewhere between 10 and 20 millikelvin. That's where the helium-3 and helium-4 come in. And incidentally, in order to boot a quantum computer, the bootstrapping process, which is basically cooling, takes about 24 hours. So running a quantum computer is not trivial, but it's not impossible. So we have several of these devices in Yorktown, in our research in Yorktown, and we have a couple here in Switzerland, in Rüschlikon. And in fact, the guys in Rüschlikon are quite heavily involved in the development, research and development on quantum computing at IBM. I'll talk about that in a few minutes. If we look at what's actually feasible and doable today at the device level. So if you look up there on the right, you see a bunch of numbers connected by little lines. And those numbers, they represent individual qubits. And the lines, they represent the capability to entangle. Okay, entanglement means physical proximity. You can entangle two qubits which are physically next to each other. Unless you're Chinese, in which case you entangle the two qubits which are physically next to each other, then you physically separate them, put them on in a rocket, send it up into near Earth orbit, and then you still have two entangled systems. But let's say for the sake of computational, using it in algorithms and in computation, they need to be physically close to each other. We have, when we talk about quantum computers, we have three important measurements, three important quality measurements, which make a good or a not so good quantum computer. And the first one, which everybody talks about, is the number of qubits. That's the one you see in the press. And that's the one that everybody is, doing their press announcements and saying, we've now got 50 qubits, or we've now got 55 qubits. And it's important, but it's not the most important quality measure of quality. As important is the error rate. The thing is, at 10 millikelvin, or at 12 millikelvin, or 14 millikelvin, there's still a temperature, there's still a finite temperature. That means the microwave resonator, or the atom, or the wave gap, which contains a standing wave, a microwave standing wave. There's a certain amount of thermal noise in there, and that thermal noise leads to errors. And managing that error rate is of critical importance. In fact, it's probably more important than making more qubits. If you can lower your error rate by 50%, then that's like adding another 50% more qubits. So a 70 qubit system with an error rate of X, in terms of its ability to perform algorithms, is more or less equivalent to a 50 qubit computer with an error rate of X over 2. The other important measure of quality is the so-called decoherence time. And decoherence means that even the best qubit, maybe one day we can get down to 1 millikelvin, or maybe even microkelvins. These qubits will still, at some point, the thermal noise will just destroy superposition. That electron will have a determined state at that point. There's no way around it. And this decoherence time for the traditional programmers among you, that's kind of like saying every quantum program you write has a finite maximum execution time. You cannot run a program which is longer than 10 milliseconds. So if you link that to your clock rate, that gives you the maximum number of quantum operations you can perform. So those three values, number of quantum bits, quantum error rate, and decoherence time, they're all of key importance. And all the money that IBM and Google and Intel and Microsoft and all the rest of us are all pumping into quantum computing, basically it's about improving those three numbers. Because improving those three numbers gets you closer to the goal, the holy grail of a universal quantum computer. Where we are right now, there are companies doing quantum annealing, which is kind of almost like a cheat, a way of doing quantum computing, which is cheating basically. We have approximate quantum computers where we are now at several tens of qubits, but we're pretty clear about how to get to hundreds or even thousands of qubits. And then at some point, we're going to have a universal false tolerant quantum computer. Now, the thing is, you can take a whole bunch of real-world qubits with error rates. You can apply error-correcting codes and Shannon's theorem and produce a perfect qubit. In order to do that, you need one perfect qubit. You need, with the current state of the art and state of understanding of how this works, you'd need a couple of thousand real qubits. But at some point in the future, we're going to have a large number of ideal perfect qubits. We're pretty clear about that. And once you really start to get the science fiction of a million ideal qubits, then you're simulating everything basically. You're talking about computer systems which can optimize the complete energy consumption of everything on Earth in real time. Every moving vehicle, every flying aircraft, every ship, everything, just more or less in real time. Where is everything? Where's it got to go? What's happened? How do I optimize for 20 different variables? And that's very, very interesting for large logistics companies or car manufacturers or people operating financial markets. I'm not even going to talk about how that changes society. That's another talk. But there's a lot of potential there. In 2016, we released the quantum experience. There are now a whole bunch of these quantum computers at various locations based on our quantum bit device. And there is a way to access that and use those quantum computers on the internet. If you just Google IBM Quantum Experience and you have a IBM Bluemix account. Does anybody have a Bluemix account here? Other than my IBM colleague? One guy here, you have one? Okay. So that's obviously a pretty clear to-do for IBM Switzerland. Is get you all up on Bluemix, because you can then play around with a quantum computer, and it's actually very easy. There are a whole bunch of worked out, explained Jupyter notebooks using Python with embedded quantum assembler, explaining how the algorithm works, which you can visualize, which you can run through, either using a quantum simulator or using a real quantum computer. In the real quantum computers, there's a 5-bit and a 16-bit, and I think a 20-bit freely available. More bits cost money, and a lot of bits cost a lot of money. So yeah, and a whole bunch of videos and yeah, the usual stuff. And if you want to get a hand up, hand-holding help actually using this and trying to understand how you might use it in daily, with daily problems. There are a bunch of people at IBM called quantum ambassadors. I'm one of them, and we come and do enablements and hackathons and all that good stuff which you already know about, onboarding. And I've been teaching this at university as well, in the University of Osnabrück and the University of Munich. It's always surprising how quickly the students understand the mathematics of quantum computing, how quickly they understand it. And it's very worrying, especially for me, because some of it I still don't really understand. So what does a quantum program look like? Interestingly, there's a significant word on this foil. And it's up at the very top. It's the word experiment. And it helps a lot to think of a quantum computing program, not as a traditional computer program, but as like an experiment. So you do a whole load of preparation. You go to the supermarket, you buy your ingredients. So that's this bit here, where you see all the Q0, Q1, Q2, Q3, and Q4. That's going to the supermarket and buying the ingredients. And then all the blue and green and yellow stuff, that's, chop the onions and weigh the flour and clean the carrots, whatever you got to do. And the little, what color is that? Pink squares with like a meter on them, that's cook. Okay? So quantum program is a bit like an experiment or cooking a meal. Lots of preparation. The actual cooking is the bit that's key, that's important. That's where all the chemical processes happen in cooking, and that's where the actual measurement happens in the quantum programming. And the algorithms, quantum algorithms, are essentially all how do you prepare your food. You can do this visually. There's a visual editor. It actually looks like this, and these are different gates. You can go into the online documentation, understand what a Hadamard gate is, understand what a X rotation, a Y rotation, and a Z rotation are, and what they do for you. We've seen extraordinary take-up with this. It's really been incredible. I think this is a simulation. No, this is a simulation. Here we go. No, doesn't want to do it. There's supposed to be a simulation with little blinks, people using the simulator. So I think 60, 80,000 usages last year, and lots of people signing up, lots of people trying these quantum experiments, lots of people just getting familiar with how you program and use a quantum computer. This is an example of what you see when you access that portal. And you can't really see it here, but you see fridge temperature 0.0138863 Kelvin. So 14 millikelvin. That's the temperature of that device. And I did that screenshot about 30 minutes ago. The temperature of the 20 qubit machine isn't shown because that's only, at the moment, only for people who are members of one of the IBM quantum hubs, or partners or members of the IBM Q network. If you were, and with my IBM ID, I'm not enabled for that. At least not when I'm showing a public talk. Then you'd see the temperature of that one as well. And there's various other options, including, interestingly, a quantum simulator based on a high-performance computing cluster. So, quantum simulator on HPC, which then is, if you're writing quantum programs, is plug-in compatible or API compatible with the real quantum computer. It's just changing one constant in your API invocation, either uses a simulator or the real thing. How does it work? Well, Hadamard gate, as I said at the start, it takes a real defined bit and puts it in a state of superposition. So here we've taken qubit 0 and we've put it in superposition. If we now measure it 1,000 times, then that's faked. I can tell that's faked because it's exactly 500 times for a 1 and 500 times for a 0. So Q0 is initialized, put into superposition, and then we measure it. Here's Q0. Interestingly, the 0 is on the right. Don't worry about it. It's just it's a convention. If we were using the real quantum computer, then I expect to see something like 497 and 503. I wouldn't expect to see 500 and 500. So we run this quantum program once, twice, a few hundred times, and we will see both possible states. If you all followed me there. Hope so. Anybody not got that? No? If we now insert a second Hadamard gate, so we reflect back, we've initialized qubit 1 to be a 0, qubit 0 to be a 0. We've applied 2 rotations, and it's rotated it back to be a 0 all the time. Now, the real challenge is, how do I use things like superposition and other kinds of rotations to write real-world solutions to problems, like factoring a large number, or sorting a list of numbers, or other things. You also see here that this is taken from a real-world example. You sometimes get the wrong answer. The really, really good quantum algorithms have the property that they are robust in the face of quantum errors. So I mentioned earlier there's this thing called Shor's algorithm, which is used to factor numbers. You take a large number and it will provide you with the prime factors. Big problem for cryptography when we get to 500 or 1,000-bit numbers, but right now it's not a problem for cryptography. Interestingly, the algorithm which was developed by Professor Peter Shor from MIT, actually quite a long time ago, before there were quantum computers, he developed an algorithm for quantum computers. Interestingly, that algorithm becomes better, less error-prone, the more bits you have. And the best quantum algorithms have that property. They're robust in the face of errors. You can also use the SDK. So the SDK is basically, this is what it looks like. You have anybody use Jupyter Notebooks here? Anybody not use Jupyter Notebooks? Okay, you need to start using Jupyter Notebooks. Basically, it's a way to program in Python where you have your program and your documentation together. And was that a comment? No, not just Python, but mostly Python. Yeah, but mostly Python. So you can access the IBM Quantum API through Jupyter Notebooks. That's native. You can download the SDK on your machine, run the notebooks locally. You can run them in a Docker instance. You can run them in a Docker instance on your own machine, in the cloud, whatever. I mean, it's all containerized. So good luck with that. It's reliable, it's robust, it works. Even I worked out how to use it. And what we have there is, well, more or less, it's not totally there yet. So it's an object-oriented class for the easy construction of quantum circuits. So you see here, wherever you see a Q, that's a qubit, and wherever you see a C, that's a classical bit. Basically, every time you look in a C, you observe. So that's the point where any operation where you see a Q and a C in the same function, that's the point at which the measurement occurs. That's the point at which your program actually gets executed. There are a bunch of examples, and those examples, this is part 1 of the screenshot. It goes on for this is section 3, 4, and 5 as well. So things like teleportation, entanglement, tomography, discrete tomography. So any fans of Sudoku here? I'm addicted to Sudoku. Or battleships, or tomography. So you can do tomography with quantum computing. You can also do quantum chemistry. There are a whole bunch of examples for quantum chemistry. So, sign up, take a look, and most of these are explained with the Jupyter Notebook in such a way that the math and the details of the algorithm are also fairly tractable. Fairly tractable because some of them will still bend your brain. Let's quickly look at 2 examples. So quantum chemistry, looking at reaction pathways, and classical traveling salesman using with Max Cut. The world has developed algorithms for quantum computers which work with these classes of problems. Now, are we at the stage where we're completely simulating a coffee molecule? No, we're still a long way away from it. But do we have a technology path which will get us there, where we know what the intermediate steps are? Yes, we do. Do we have a way to simulate molecule geometry? We do for very simple molecules, and we have a technology path which would get us to complex molecules. The use cases here are fairly obvious. You know that you're running, these are the kind of problems you guys are running as well. So the pharmaceutical industry is really, really hot about this. Traveling salesman and Max Cut, basically the entire new economy from Maersk and Amazon to DHL and I don't know, Schweizer Post. They all got to be interested in this because that's optimization and routing and complex network optimization. So we have algorithms which are capable of working in those domains. They're just not at the scale where we can use them for those real problems yet, right now. What we typically do is use the quantum computer to minimize the energy of some system and have that working with a classical computer to choose a new value of the state to try and optimize. And that's one of the kind of conceptual barriers that we have with quantum computing is that there is no sense of having a bunch of data which I analyze. So traditionally I'd have, I don't know, a database or a Hadoop or whatever, some large amount of data which I would do an analysis on. In quantum computing, it works the other way around. You define a state space, and in the algorithm, you implement what you're trying to find. Let's say conceptually, that's the point where most people start. Most people, at least in their minds, they go, "Wait a second, I don't get that." But that's a kind of an attempt to bridge that conceptual gap. And right now, that's where most research onto using quantum computing for real-world problems is going. I'm going to, in the interest of time. Yep. So where are we right now on the way to so-called quantum advantage? Quantum advantage is, we define as a particular point where quantum computers, for at least maybe even just a small class of problems, become computationally much more efficient than traditional computers. That's the point where, if your problem belongs to the class of problems which have quantum advantage, then it's pretty stupid not to buy a quantum computer, because it's going to solve the problem faster than any classical computer can. And we are pretty close to quantum advantage, at least in quantum chemistry. We're not quite there yet with optimization and max cut and all those other problems, but we're going to get there soon. So that's what everybody's hoping for. When you see press releases not from IBM, but from our competitors, you will see them talking about quantum advantage. That's kind of like, that's the point where we now have a very solid commercial, monetary advantage, where we say buying a quantum computer, running real-world problems on it becomes significantly more efficient than investing in traditional computing resources. And that's the point, of course, where everybody in this room should start to be nervous. And if you're not nervous, you should be, because that's going to happen. And the class of problems that are going to become tractable and are going to become achievable with quantum advantage is not going to get smaller. It's going to get bigger and bigger and bigger. It's going to encroach on what you're doing. So this is it doesn't look like a computing center, but it is. It's a computing center with some research, a research bent. I don't know whether this was taken in Yorktown or in Rüschlikon. Could theoretically be Rüschlikon, but you can see one of the machines here. It's a quantum computer. And that's something, I mean, that's not something we're going to roll out in the foreseeable future, where you can go to your local computer center and buy one of these things off the shelf. I'm sure that will happen at some point in the middle or distant future. And I'm sure we're going to have a lot of progress on getting these things reliably and safely and robustly cooled down to the temperatures they need to be at. But that's what it looks like. And for Gilad, another photo with a backdrop of plants. And if you want to see one of these things for real, then basically you can do that here in Switzerland. You just need to get invited or ask nicely and come to Rüschlikon. I'm sure they'll be very happy to oblige you. That's in Rüschlikon. This is all running at microwave frequencies, by the way. So if any electronics engineers here who are familiar with microwave electronics, then you'll understand how this all works. So microwaves running at millikelvins. Yeah. Just briefly, the IBM Q network. So this is my obligatory pitch. Anybody here or anybody who's not already talking to IBM about this, you should be, or we'd like you to. And there is a quantum hub being established now in Oxford, in England. There's probably going to be one in the near future in mainland Europe. I don't know about any concrete plans in Switzerland, but who knows? CSCS would be a very good candidate. How long have I got? Okay. Minus. Okay. Then I skip. So I just wanted to briefly talk about something that's happening at IBM Rüschlikon. They're working on a whole bunch of stuff, improving coherence, working on quantum simulators, improving the control software and hardware. I mean, running one of these things is not trivial. You have to do just keeping it up and running and at the right temperature and stable is a huge headache. But in Zurich, they're also working on optimized 2-bit qubits. So they're looking at XX, YY, and ZZ transformations. So won't go into the details, but that makes a quantum computer potentially a lot more efficient than what we currently have. And to do that, they use a flux-tunable coupler. And we already know about that. That was in Back to the Future, the flux capacitor. So not only do we have the Vogons eradicating the Earth 10 minutes before it came up with the answer to what is the question, to which the answer is 42. But we also have Back to the Future, who predicted the future. This was used for time travel. We're going to use it for better qubits. But maybe better qubits are a way to time travel. Who knows? So at that point, I will finish. And if you're interested in learning more, those are 4 books I can very much recommend. From the hardcore physics on the left, most of you, if you consider yourself programmers, you need to read Mermin's book. It's a very tractable introduction to quantum computing. There's very little physics in it. There's lots of algebra, but done in a way which, if you can program a computer and you know Python or C, you get most of it. One of the things that about quantum computers is that all the business happens when you observe, which raises some very, very scary questions about what does it mean to observe. And then you're in the area of systems theory, and the book by Macy or the classic by Schrödinger for when you can't sleep at night. I recommend those. So thanks. I hope at least you took a little bit away about quantum computing. If you want to know more and you want to get involved or you want to actually do some programming, then contact me offline. Thanks.